Hello?
Yes.
Okay, hold on. Share whiteboard. All right. Be red. Now let me just copy everything. Here. 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 Text. Here. Text. Here. Here. None. All right.
You can see the stuff that I'm writing, right?
Yeah.
Okay. I can't seem... I'm not able to edit the text boxes for some reason, but that shouldn't be an issue.
If anything, I'll just like stop my share and then you could do a new share.
Yeah.
Okay. Ready?
Okay, we are recording. Yeah, let's do it.
All right. Hello, everyone. I'm Isaiah.
Hey, everybody. I'm Hassib.
And this is our final virtual SI session for this semester for Phys49. And in today's virtual SI session, we'll be going over forces. So since we've been doing forces for a while, we'll just explain the very basics like Newton's second law and then go straight into problems. So the point of forces is to show the relationship of how an entity moves a mass, and we could quantize that by using Newton's second law, which says that the sum of forces is equal to the mass of the object times the acceleration. And this equation is the one we use the most in forces. One thing to keep in mind is that forces are a vector quantity and they have a direction. So with that like basic overview, the best way to learn about forces is to apply them in a problem. So let's go over our first problem, which is a box and an incline. Okay. I'm just going to delete this. Okay. So here is the first problem. Oh, not that. It's this one. Right. So a box that's 30 kilograms is being pulled up a ramp with a 40-degree incline. If the box starts from rest, what is the final velocity of the box at the top of the ramp if it takes 3 seconds? So what's something we should always do first, regardless of the physics problem itself? What's step one?
And that's a question for everybody in the chat. What's the first thing you have to do when it comes to these type of problems?
Or any physics problem in general.
Just to note for everybody listening, in order to contribute to the chat, you have to pop up the chat window. you could go to meetings from the menu on top, and there's an option that says show chat, and if you clicked on that, it will show the chat, and you can type in stuff and answer our questions. Okay, so I think when it comes to the physics problems, the first thing is probably sketch something, is to get an idea about the problem.
Yeah, so that's what we're going to do. We're going to sketch out this ramp. Ooh. Right, go like this. And that should be okay. And then we want to put all the information we have from the problem. Oh, wait, I forgot one thing. Part one is, oh, I guess I can't draw a box like that. Is this here? Here. And right there.
There you go.
Right. There you go. And now we want to put in our other information. So we have a 40-degree angle here. And we also want to put the direction, our coordinate system. So let's have this way is positive and this way is positive, where this is the y. So like this. And then this is the x. Let's push this up more so we have room. Okay, there you go. So now we have a general picture or sketch of what's going on. With forces, we want to do something called a free body diagram. And what those are is just, it's showing what forces are being acted upon the object. So if we see from the problem, we have a pull force. Let me add, pull up a ramp with 15 newtons. We have a pull force of 15 newtons, and that's all the, I guess, outward forces that are being put upon this box. However, we got to consider normal force and weight. So let's start with the pull force first. Let's move this up here, this over here, and this over here. All right. So we have the pull force. Call this F pull. All right. And now we got to deal with weight and normal force. Now, normal force, you would think it would go up like this. However, the definition of normal force is a support force perpendicular to the surface. So it goes straight up like this. All right, we'll call this big N. And now we have weight. Weight always goes down, right? So we're gonna go like this. Now, the thing with weight in this case is it doesn't agree with our current coordinate system. So what we're going to have to do is break it into components in order for it to agree with it. So if we use this 40 angle, we could do some tricky geometry to break this into components. So I'm gonna label my components as, let's do pink, and then this is going down, and then and right here. So using geometry, you know that the 40 is right here as well.
So the purple, the pinkish arrows are the components of the weight.
Yeah, and we want to do that is because with our coordinate system being on a slant, we want our weight being on the slant as well.
Okay.
So everything agrees with each other.
Mm-hmm. And that the pinkish 40 degree, that angle would always be equal to the angle of the ramp, right?
Yeah.
If we
And
apply the geometry rules, we will end up with equal angles.
I believe it's alternate interior angles. That's the law, but pretty much, yeah, it's going to be like this.
Okay.
So now we have all of our forces labeled. What we want to do is start applying Newton's second law. So what was Newton's second law again, to everyone in the chat? Again, to open up the chat,
you have to
for Mac, or go for it.
Yeah, you have to go through a meeting menu on the top left. If you clicked on it, the drop-down menu, you choose the option called Show Chat, and that will show the chat box where you guys can type in the answers. And the question again is, you guys can type in what's Newton's second law. We'll
I
take.
think the shortcut for show chat is Command-Shift-H or Control-Shift-H for.
Okay, yeah, that's useful.
So we want Newton's second law, how to quantize all the forces.
All right, so one of the answers we got is weight equals mass times gravity for Newton's second law.
So weight isn't necessarily a law itself. It's just a representation of the gravitational force on an object.
Yeah, and I think weight equals mass times gravity. That's the special case of Newton's second law. Like if we replace the force on the left by the weight force and the acceleration on the right by gravity, we will get weight equals mass times gravity. But that's the special case of Newton's second law. There's probably the more general case for the law, and that would be the sum of forces in a certain direction will be equal to the mass times acceleration.
Exactly. So F is equal to ma. That's pretty much the general case. Right here. And I'll try my best to make a sigma because that's important. Because it shows the sum of forces.
Yeah.
There you go, close enough.
Yep.
So now we have this, and remember, Forces are a vector quantity, meaning it's direction dependent. Let's go like that, like that. So what we want to do is sum the forces in the x direction and the y direction. So let's start with the y direction actually. So f underscore y is equal to, so we have normal force, and we also have this component of weight. And this component of weight, if we remember our decomposition of vectors, that since this arrow is on, or where's my pointer? Since this arrow right here is on the adjacent side of the angle, we could say that this is weight times cosine of 40. And since this, since this is the opposite, we could say this is weight sine 40. So continuing on with our sum of forces in the y, we have normal force, and we also have the component of weight. And since it's going down, which is opposite of our coordinate system, we'll say it's a negative. Now, we said that F is equal to MA, but that's only if the object is moving in that direction. Is this object moving in the y direction at all? So is it like floating up and down? In this case, it's not, right? It's staying on the ramp and it's not levitating or anything. So there is no acceleration, meaning this is equal to 0. So with the y direction done, we're going to go into the x direction. Actually, let's do this. F underscore x. So we have the pull force, and we also have the component of weight in the x component of weight, which is omega sine 40. Now, the box itself is moving along the ramp, so therefore we have an acceleration. So this is not equal to 0, it's equal to m dot square x. And these are your two equations, one in the y and one in the x. So for now, our y equation isn't going to be used as there is nothing really to solve for besides normal force. So we're really going to emphasize the x component of this equation. So
Isaiah, I just want to point out something. So it looks like in this problem, we did something similar to what we used to do in the kinematic problem, especially the projectile motion. It's like we separated our situation into the two dimensions, like equations in each dimension, the x and the y. And we took the dimension that we were interested in and we start solving for it. So that's like a point for everybody. It's like we're not doing something very different than before. It's something similar to the kinematic stuff we're doing. We're separating the forces into its dimensions, and we're picking what's most what will help us in getting what we want in this problem.
Exactly. So the reason why we do this is because force is a vector component similar to velocity being a vector component. They're direction dependent, meaning you could break them down into their x and y components. And like Hassib said, similar to projectile motion, we're using out of the x and y, we're using what we need more, or what will help us in the problem above. So if we're focusing on yellow, if we're focusing on, yellow's a bad color. We're focusing on this equation, the x. What should we solve for? And that's a question for the chat.
All right, so for everybody in the chat, if we're using the sum of forces in the x direction equation, what would be the variable that we should solve for in order to get in order to help us to get what we want in this problem, which is the final velocity at a certain time? What would be the variable that is of an interest for us? We'll take 30 to 40 seconds. All right, so I mean, if we're using it in the x direction here, and we want velocity, and we have a force, we know that the force is going to cause acceleration.
Mm-hmm.
Acceleration is the quantity that changes velocity. So if we're looking for velocity, we probably need to find acceleration first, and that would probably be our variable of interest in that equation.
Exactly. So
Probably also during the process we need to find the x and the y component of the force, and we already have it written down as the x component, which is the weight times sine 40.
yeah, so if we do some algebra, all we have to do is divide all of this by the mass. And let me actually move this here. Actually, no, this is good. Yeah. And another reason why we want to solve for acceleration is because if we look at all these variables, and let's just look at the x equation, the only thing that's missing a value is acceleration itself. We have mass, we have weight, and we have F pull. F pull is equal to 15 newtons minus, we said that weight is mass times gravity. So we're going to do 30 times 9.8 times sine 40. And all of this, let's use brackets, divided by m, which is 30 kilograms. Go like that, yeah. And then that should equate to,
All right, I'm doing the calculation right now.
well, it'll be negative 5.8 meters per second squared.
I got negative 5.8. Doesn't that seem weird a little bit, or not really? Actually, you might not. It's not super weird. That means the object is accelerating downward, right?
Yes, that's correct. So that's just saying this box is really, really heavy and it's going downward. So we're going to change this problem a bit because that just makes it complicated. We'll just do like, okay, so if it's 30 kilograms, let's say it's being pulled with
Yeah, so this for everybody in the chat, the situation that we ran into is that the force is not enough to pull the box up the ramp. 15 newtons wasn't enough to pull the box up. So we're just gonna make the box a little lighter and we're gonna make the box a little bit heavier. So
Yeah, so what we're doing is making the pull force stronger and then making the box have less mass. So we'll do 15 and then say 150 newtons. Yeah, okay. Over 15 kilograms. Right, okay, yeah. So F pull is 150 newtons minus 15 times 9.8 times the sine of 40 divided by 15. And you should get 3.7?
yeah.
3.7 meters per second squared. Okay, that makes more sense. So now we have an acceleration in the x. So the goal is to find the final velocity of the box when it reaches the top of the ramp if it takes 3 seconds. So all this sounds like a kinematic problem. So what we're going to do is make our table, right? And then here, and then right here, here. All right, cool. We'll say this is initial, final. Or not initial and final. Let's do top of block, top. And then we have time. We have velocity. We have, since we're only doing x, we'll do x. And we have acceleration. So initially, this is, let's do select. This is 0 seconds. And then the top, we don't know. So we'll say time underscore top. Velocity, since it starts from rest, it's 0 meters per second. And then this. And we will say that this is V, we'll just say V top. And that's what we're trying to find, the velocity at the top of the ramp. X, we'll say 0 meters. And we'll say X underscore top because we don't know that. And then it looks like we have a question in the chat that says, where does the 15 times 9.8 come from? So we said that weight is equal to mass times gravity. And we need weight in our omega sine, or weight sine 40 component. So we just place our mass, 15, our gravitational constant, 9.8, and then times sine 40. That's how we got it. mg, correct. And our acceleration we found, which is acceleration, which we found was 3.7 meters per second squared. And then since this is a constant acceleration, it's the same throughout.
This problem It's like it transformed into a one-dimensional kinematics problem.
That's exactly what it is. We're using the relationship of forces to find a missing variable and then finishing the problem with kinematics. So using our kinematic equation sheet, what would be the best equation to use in this case? Let's type that up in the chat. We'll give you 30 seconds.
All right, what's the best equation for us to use to find what we want, which is the final velocity?
So from a kinematic sheet, the best one to use would be V final is equal to V initial plus, let's make these lowercase,
I have it right here.
plus acceleration times t. And what we're trying to find is, let's move this over a bit. And what we're trying to find is v underscore fx is equal. We're trying to find v final, which in this case is v top, is equal to v initial, which is 0, plus 3.7 meters per second squared times time. And we see that this takes 3 seconds to reach the top.
Mm-hmm.
And then when you calculate that, this equals, should get v underscore top is equal to 11.1 meters per second.
All right, so it will be 11 meters per second at the top of the ramp. For everybody following with this problem, you probably have to notice that we don't care how long is the ramp. We don't care when does it end. The only thing we know is in 3 seconds, the object will be at the end of the ramp. So you can go and calculate distance and everything, but that's not for any importance of us. We just know that the object will be at the end of the ramp in 3 seconds, and we just utilize that piece of information to get the final velocity. And Isaiah here got 11 meters per second, and that's the velocity of the object at the end of the ramp.
So to quickly overview what we just did, we drew our picture, we created our free body diagram, which shows which direction the forces are and what forces we have. We broke it into y and x components. We realized that the y component wouldn't be any use, so we only use the x component. And within the x equation, we see that we got to solve for acceleration because that's what's going to be used in our kinematic equations. So we isolate for a of x, and we get 3.7. Let me write that out actually, that acceleration here. I'm just going to write it more clearly. 3.7 meters per second squared. Move this here. And after we found acceleration, we created a chart like we do with our kinematic equations. And we realized that within this chart, that the box starts from rest, so it's 0. We're trying to find the velocity at the top. And we don't care about, we do know time top, which is 3 seconds. And we don't really care the dimensions of the ramp itself. because we could easily solve for velocity without it. And using this equation from our kinematics list, we could isolate for v top or v final, which is v top, which ends up being 11.1 meters per second.
All right, I guess it's the time to move to the second problem. So our goal of this session was to present some type of moderately challenging problems when it comes to forces, and that was the first one, which is a box on a ramp. The second problem that we will work on is an elevator problem. I don't remember working on any elevator problems in the class except maybe one that was mentioned in the slides. So now we will. I have an elevator problem, a simple one as a start, and let's work on it.
So I'm gonna stop sharing my whiteboard so Hassib can share his. Yeah?
Yeah. I think I can do this.
All right, go for it.
This.
There you go.
All right, we're in business.
Mm-hmm. Again, yeah, Hassib will be blue and I'll be red. Mm-hmm.
Okay, is the text too small on your screen or is it readable?
Yeah, it's pretty small.
Okay.
Actually, no, it's fine.
Yeah?
Yeah, it's fine.
Okay, just a little bit better.
Okay, yeah, that's better.
Okay, this will be a simple problem as far as elevator problems can go. We have a person standing on a scale in an elevator. The person's weight is 75 kilograms, and that's the only thing we know about the initial situation. As a start, we will draw something. We'll draw a sketch. This will be the escalator.
A little note. Mm-hmm. The person's mass is 75 kilograms as opposed to weight.
Yes, that good catch. Mass is always the quantity that has a kilogram in it. Weight is the one where we take the mass multiplied by acceleration.
Yeah. So weight is a force due to gravity, and mass is the amount of matter something has. That's just the main difference. The easiest way to tell is, like Hassib said, mass has the units of kilograms, and weight is in units of force, so like newtons, pounds, etc.
And drawing a person in this is so hard.
It's okay.
All right, that's
pretty good.
Yeah, that's good. Looks like me. Okay, so we know that the mass of the person is 75 kilograms. So that means we have a force going downwards, which is the force of the weight. And it will be described as W. And we know that there is a normal force going up that supports the person. Like this. And that will be our normal force. And just by reading the first line of the problem, we can say that our weight is equal to mass times acceleration of gravity, and that will be equal to 75 times 9.8, and that will give us...
I got 735 newtons.
735 newtons. And that's the only piece of information that we have so far. Now, the first question is, what is the reading of the scale if the elevator is moving upward with an acceleration of 3 meters per second squared? So right now, another piece of information we have is our acceleration. It's in the y direction, and it will be 3 meters per second squared. And that means the elevator is lifting the person up. It's not showing as a force, but it manifests itself as an acceleration. And we need to figure out the reading of the scale. One very important rule when it comes to the elevator problems, I will put that in red and in bold too, is that the scale of the elevator reads the normal force. That's the job of the scale on the elevator. If we were standing in an elevator and we're looking at the reading, the scale will give us the reading of the normal force. Here, since the elevator is moving upward, the normal force will not be equal to the weight. And we can see that by simply applying Newton's second law. So as we went over a little earlier, Newton's second law will be sum of forces is equal to the mass times the acceleration.
So, see, in this problem, are we saying that up is positive or down is positive?
Okay, good one. Here, as usual, we need to specify our coordinate system first. So we will say that upward is positive. Oh, that's too. We will say that upward is positive. Let me erase this one. And that's probably the only dimension we're interested in. There is no motion to the right or the left. So that would be it. So yeah, upward is positive, and we know that forces are vector quantities, so direction will matter to us. Now, finding the sum of forces will equal to, and in the y direction, we have two forces to worry about. The normal force, which is in the positive direction of the y, and the weight, which is in the negative direction, so it will have a negative sign, and it's a w. If we want to break it down a little bit more, it will be the normal force minus m times g, because that's the breakdown of the weight. So that's as far as the left side of the equation. And since we have it ready, we can start working with the full equation. The left side is the sum of forces, so we have n minus w, and that's equal to the mass times acceleration. And if we looked at this equation, we don't know the normal force. We know the weight because we calculated it earlier. We know the mass of the person, and we know acceleration because it's given in the first part of the problem.
So realize that in this equation, in this problem, the sum of forces in y doesn't equal 0 because it's moving along the y-axis. So if we were to do sum of forces in the x, that would equal 0 because this object is not moving left or right.
Mm-hmm. And we can see that by noticing that there's no forces pointing to the left or the right. That means there's no motion or any net force happening in the x direction. And we all know that elevators just move up and down. They never move left and right, unless they make one in the future that moves left and right.
That's all your guys' jobs.
Yeah, okay, I'll take it. All right, so in the y direction, as Isaiah said, there's the net of forces is not zero. It's going to be non-zero net force because the elevator is moving in the y direction. We know that the elevator is moving up, and from our intuition, if we actually go to an elevator, put a scale, stand on it, and the elevator will be moving up, the scale should read a value that is bigger than our weight. And we'll see if that's the case once the normal force. So let's start calculating the normal force, because the part A asks us for the reading of the scale, and the reading of the scale is always the normal force. So we have to go for the normal force. So N equals W plus M times A. All right. And N equals W, we calculated to be 735 newtons. And the mass of the person is 75 kilograms. And we have to multiply that by the acceleration of the elevator, which is 3 meters per second. Another note here is we know that the elevator is moving upward. So the acceleration of the elevator is upward. And that will be the arrow for the acceleration. That means the acceleration is positive. So we substitute it as a positive number in the equation. So this is the equation that will give us the values for the normal force. So just a quick calculation, 735 plus 75 times 3 will give us,
I got 960.
Will give us 960. That's correct. 960 newtons.
And so you see that the normal force is greater than the weight itself. So this shows that the normal force is not always equal to the weight. And in this case, this is why in an elevator, when you go up, you feel like something's pressing down on you, or you feel heavier. And that's because the normal force isn't equal to the weight. It's also taking account of the acceleration of the elevator.
Yeah, and we can notice that technically by looking at comparing this value and this value right here. So the person on the scale will see 960, but the weight of that person is 735. All right, so that's the situation where the weight changes. This is a common situation in elevator problems. So this it's very important to understand it. We'll move on to the, let me say this, if anything is unclear with this, you guys can type it in the chat. I will move to the second part of this problem, which is an elevator that is moving, but the elevator is moving down with a constant speed of 4 meters per second. And I'm going to put some emphasis on that it's constant speed. All right, let me see how, I'm probably going to erase the word problem. That will be this way. And I'm going to leave this except acceleration, and that's it. Okay, with the second part, again, we know mass is equal to 75 kilograms. Weight is equal to 75 times 9.8, and that was equal to 735 newtons. And we also know a constant speed of 4 meters per second. And right now, we need to know the reading of the scale. So the same thing we did earlier is we're just going to apply Newton's second law. And to apply it, we need to find the sum of forces in the y direction. And in our situation, we have two forces again. We have the normal force, and we have the weight in the opposite direction. And the weight is pointing downwards, and our positive is upwards, so the weight will be negative. But when we start looking at acceleration and in Newton's second law, and that's a question I want to ask everybody. What is our acceleration in this problem, given that our speed is constant?
We'll give you about like 30 to 45 seconds for this.
Mm-hmm.
So from the chat, we have that acceleration is 0. And we could say that this is correct because the behavior of a constant speed is what?
The behavior of a constant speed is that there's no acceleration affecting it.
Yeah, the speed is constant, so it's not changing. So there's no change maker. Therefore, acceleration in a constant speed is 0.
Okay, so we can see that here we can utilize a lot of the ideas from kinematics, and that's where it's the type of problems where a lot of the ideas we took before intersect with the new ideas, and that's the beauty of physics. Is like eventually everything will work together. So we'll go back to the problem. Acceleration is 0 then. If we want to apply it to Newton's second law, that means this is the mass, but our acceleration is 0. Isaiah, can you see what I'm typing right away?
Yeah.
Okay. And that means our law will end up this way. In Newton, the normal force minus the weight will equal to 0 because our acceleration is 0. So this is very important to realize that the elevator is moving. There is motion happening. But just because the motion is constant, that means there's no acceleration and there's no net force. All right, so let's keep solving for the normal force. Just we add the weight value to both sides, and that will give us the following, that the normal force is equal to the weight. And that means the normal force is equal to 735 newtons.
So what this shows is that, so when you get on an elevator, and let's say you're going, regardless if you're moving up or down, when you're on the elevator for a while, your speed becomes constant. And that's why during your elevator ride, you feel normal again. And that's because there's a constant speed and there's no acceleration.
Exactly.
So in the first, go for it.
Yeah, that's actually technically correct, because when you go to an elevator, you feel the force on your body like right when the elevator moves, but after a couple seconds of the motion, you don't feel anything anymore because it's constant motion.
Yeah. So regardless of if you're going up or down, initially you're gonna feel either heavier or lighter depending on the direction of the elevator. But once the elevator ride prolongs, your speed will become constant and therefore you just feel normal.
Okay, so I feel like putting I feel like putting a rule that we can end the session on, which is this. If there is acceleration, the weight changes.
Mm-hmm.
Can you see the sentence that I typed?
Yeah.
So if there is acceleration, weight changes, and that will be regardless of the direction of motion. That's one. No acceleration will give us no change in weight. And the third takeaway we have in this problem is scales always read a normal force. Yep, that will be the 3 points to keep in mind when it comes to the elevator problems. If there is acceleration, there is going to be a change in weight. And when we say change in weight, that doesn't mean the weight of the person. It's the weight that the person feels, because it's not like we're adding more meat to the person. It's just the way the person feels is that will be changed, and we can detect that change using a scale. If there is no acceleration, that means motion is constant, or vice versa. No motion is constant, that means there is no acceleration. That means there is no change in weight. And always scales and elevators read the normal force. They don't tell you your weight. They tell you the normal force acting upon the person. And that would be our elevator problem. There's more complicated elevator problems that we can have, but that would be their introductory problem to elevator problems.
And the beauty of these elevator problems is that you actually feel it in real life. So it's not just like something we're just spouting at you, it's actually applicable.
Yep. And,
just like many of these force problems.
All right, and Isaiah, I think you said that this is our last virtual problem.
This is our last virtual SI problem, and this is actually the most people we've had, so thank you all for coming.
Thank you, everybody, and we'll end it right here. Good luck for everybody in the finals, and for everybody who comes to our physical sessions, we will see you guys there.
Yeah, reminder that this week is our final physical SI sessions.
Yeah, this week. Yeah, actually, you're right. This week we'll have our final sessions. Also, another reminder: we will be sending out surveys to everybody as part of the final end of semester surveys. You guys' feedback is always appreciated. We want to always make these sessions better and better. And I guess that'll be it.
All right. Thank you again. Thank you all again for coming, and we will see you this week.
All right. Thank you, Isaiah.
Thank you, Hassib.
Bye-bye.
Bye.